All right, welcome back, everyone, to another deep dive.
Yeah, good to be back.
You know the drill. You send us the interesting stuff. You send us the research papers, the blog posts, the articles.
And we read them.
We read them, and then we give you the need-to-know info,
The core ideas
the core insights.
distilled down.
Today's deep dive is brought to you by a listener.
A listener question.
A listener request. Someone sent in some excerpts from Stephen K. Reed,
Oh, yeah, I read that one.
The Structure of Ill Structure.
Well-structured problems revisited.
Problems Revisited.
The good one.
It's a good one. And basically, the listener wanted to know, okay, what are the big differences between these two kinds of problems? You know, on the one hand, you have these well-structured problems like, I don't know,
Puzzles.
puzzles like a Rubik's Cube,
Algorithm.
yeah, something where there's a very clear solution, there's a very clear path to get there,
Or at least a clear way to know if you're getting closer to the solution.
versus these ill-structured problems, right, where it's kind of fuzzy.
Right, like design problems.
The design problems are, you know,
Ethical dilemmas.
ethical dilemmas. Yeah, there's not one right answer necessarily.
It might even be hard to define what the problem is in the first place.
Totally. So our mission for this deep dive is to take these two categories.
Well-structured. Ill-structured.
Try to nail down what are those core differences between the two.
But also some surprising similarities in how we approach solving both kinds.
Right, because even with those fuzzy, ill-structured problems, there are still thought processes, there are still strategies
Heuristics.
that we can use to, help us navigate that space.
And make better decisions.
So think of this as your cheat sheet,
Your shortcut
or like a map.
to understanding the landscape of problem solving.
Exactly. So we're going to be looking at how we even represent these problems in our minds, right? Like, how do we mentally picture them? How do we search for solutions? What are those steps we take? And hopefully along the way, we'll trigger some of those aha moments.
The light bulb going off.
Exactly. The listener told us that they really enjoy those moments.
Who doesn't, right?
So let's get started. Why don't we start with well-structured problems?
Okay. Well-structured problems, or WSPs for short.
WSPS. So this idea really takes off with Herbert Simon's work.
Right. Yeah, back in the 70s.
Mm.
And initially, Simon kind of saw ill-structured problems, the ISPs, as sort of a catch-all category.
Oh, really?
It was almost defined by what it wasn't, if it didn't fit neatly into the box of a well-structured problem.
It's like defining light by saying what isn't dark.
Yeah, exactly. So in his 1973 work, Simon outlined these 6 characteristics that define these well-structured problems.
Okay, 6 characteristics. Lay 'em on me.
All right, so first of all, there's got to be a definite way to test if you've got the right solution.
Okay.
Some clear criteria. Second, it exists within what we call a problem space.
Oh, okay.
Think of it like a maze.
Okay, a maze. Got it.
You've got your starting point, your initial state,
Mm-hmm.
you've got your goal state,
The exit to the maze.
exactly, and then there's all the possible paths in between.
All the twists and turns.
The third characteristic is that the moves you're allowed to make, the way you can get from one point in the maze to another, those are also clearly defined.
They're part of the structure of the maze.
Right. And fourth, any information you might learn along the way, anything relevant to solving the problem, can be represented within that problem space.
Okay.
Fifth, if the problem involves something in the real world, the way things change when you make a move within the problem, these should mirror how they change in reality.
So it's got to accurately reflect the real world rules.
Exactly. And finally, solving the problem should involve a doable amount of mental calculation. You shouldn't need a supercomputer to figure it out. And the information you need to solve it should be available without having to do an impossible amount of searching.
So it's manageable. It's something that our brains can handle.
Right. It's bounded.
Okay, so that's a pretty solid description.
A framework.
A framework, yeah.
Yeah.
So give me some examples of, like, what are some classic well-structured problems? What are those well-oiled machines?
Okay, well, you've already mentioned the Rubik's Cube.
Yeah, that's a good one.
And then there are those classic algebra problems, factoring quadratics,
Oh, yeah.
where you have to find those two numbers that add up to one thing and multiply to another.
And you can plug them back in and see if it works.
Exactly. That clear way to test your solution. And then there are logic puzzles,
Ooh, I like that.
like the classic missionaries and cannibals problem.
Oh, yeah, the one with the boat in the river.
That's the one. 5 missionaries, 5 cannibals trying to get across a river in a boat that can only hold 3 people at a time.
And you can never have more cannibals than missionaries on either side, right? otherwise.
Well, you know,
That sounds like a bad situation.
not ideal. So this missionary cannibal problem, the 5MC as it's sometimes called,
5MC, get you.
it's a great way to really visualize this idea of a problem space.
Okay.
Back in '76, Simon and Reed, they actually mapped out all the safe combinations of missionaries and cannibals on each side of the river,
Ooh.
all the possible legal moves you could make with that boat. And they published this diagram, figure 1 in their paper. It's like a roadmap of the problem space.
Okay, a roadmap. So what does this roadmap tell us about the 5MC problem?
Well, for one thing, it shows us that the shortest, most efficient way to get everyone across takes at least 11 trips back and forth.
11 trips, wow.
And what's interesting is there isn't just one single perfect path. There are actually multiple solutions, multiple ways to achieve that minimum of 11 moves.
Okay, that's interesting. So even though it's a well-structured problem, there's still, like, some flexibility?
Right. There's not always just one right answer, but there are wrong answers.
Right. And the roadmap shows you those.
It does. The problem space also reveals these dead ends, like places you could end up where you'd have to backtrack to keep going. State J in their diagram. That's a classic example of getting stuck.
Okay, so the problem space is all the possibilities,
All the legal states.
including the wrong turns. Now, you also mentioned this idea of a search space.
Right.
How is that different?
So the problem space is kind of like the theoretical map. It's everything that's possible within the rules of the game.
Okay.
The search space is the path you actually take as you're trying to solve the problem.
It's the specific moves you try.
Exactly. The ones you consider, the ones you maybe try out and then backtrack from.
Mm-hmm.
It's your journey through that problem space.
Okay, I get it. So it's not just about how big the problem is, it's about how efficiently you can search for the solution.
Exactly. Newell and Simon, they pointed this out. If your search can stay focused,
Stay on track.
right, stay close to the path that leads to the goal,
Yeah.
then the size of the problem space matters less.
It's like, it's not just about how big the haystack is, it's about how well you know where to look for the needle.
Perfect analogy.
So how do we actually search these spaces, these well-defined mazes? How do our brains do it?
Okay, so there's this general model for problem solving that was proposed by Gick back in 1986, and it's still a really useful framework.
Okay, 1986.
It starts with building a mental representation of the problem.
A picture in your head.
Right. You got to understand what you're trying to achieve,
The goal,
the constraints,
the rules.
the information you have available. And sometimes, if the problem feels familiar, this representation might trigger what we call a schema.
Oh, schema. Okay, so schema is like
It's like a mental shortcut
a pre-built framework.
based on your past experience.
So like if you've done similar logic puzzles before,
Right. You might recognize a pattern,
I'd be like, oh, I know how these usually work.
and that can drastically reduce the amount of searching you have to do.
Interesting. So schema is like, it's drawing on your experience to kind of cut to the chase.
Exactly. But if there's no handy schema available, then we have to actively search for a solution.
We got to roll up our sleeves.
And for that, we often use what are called heuristics.
Heuristics. Okay, so these are like
They were like general problem-solving strategies,
Oh.
things like means-end analysis
means-end analysis.
and breaking the problem down into sub-goals.
Okay, sub-goals, got it. So means-end analysis, that's like,
It's like constantly checking where you are in the maze,
mm-hmm.
comparing it to where you want to be,
The goal.
and then trying to reduce the difference between the two.
So you're making moves that get you closer to the exit.
Exactly. And sub-goals, those are like mini goals along the way,
Okay.
breaking that big problem down into smaller, more manageable chunks.
So it's less intimidating.
Exactly. Like with
Wow.
that 5MC problem, remember,
The cannibals and the missionaries.
one possible sub-goal might be, okay, let's try to get 3 cannibals across the river first.
Right.
And Reed and Abramson, back in '76, they actually found that giving people that specific sub-goal really helped them solve the 5MC problem.
Oh, really? Just that little nudge?
Yeah. It reduced the number of moves they needed and the time it took to solve it.
Okay, so sub-goals. Mental breadcrumbs.
Yeah, exactly. Leading you through the maze. Now, these heuristics, they're powerful tools,
Mm-hmm.
but they don't guarantee a solution.
They're not foolproof.
Right. And then there's another big player in problem solving, especially with well-structured problems. Analogy.
Analogy.
Basically, it's about looking for a problem you've solved before that's similar to the one you're facing now,
Okay.
and then trying to adapt that old solution to the new situation.
So using past experience to tackle new challenges.
Exactly.
Mm.
And Gick and Holyoke, they found that solving these analogous problems, it can actually help you build those schemas we talked about.
Oh, interesting. So, like, by seeing the connections between different problems, you start to develop those mental shortcuts.
Exactly. You build up that library of problem-solving patterns.
Yeah. Makes sense. Okay, so we've got this framework for problem solving. We've got the problem space, the search space, heuristics like means end analysis and subgoals, and this idea of analogy. Now, how do these actually play out in the real world?
Okay, well, let's look at some specific examples,
Yeah, let's get concrete.
starting with puzzles.
Classic puzzles.
So with puzzles, representation is key. How we picture the problem in our minds, how we organize the information, that really impacts how we approach solving it.
And Simon, he did a lot of work on this, right? With the Tower of Hanoi puzzle?
Yeah, the Tower of Hanoi.
Mm.
3 pegs, different sized discs. You got to move all the discs from one peg to another, following specific rules.
Yeah, you can't put a bigger disc on top of a smaller one.
Right, and you can only move one disc at a time.
Yeah.
So in 1975, Simon, he explored how different ways of representing this Tower of Hanoi problem in your mind affect how we solve it. He identified 3 main strategies. One focused on the final goal,
Okay.
like always working towards getting that largest disc to the target peg.
Makes sense.
Then there was the strategy based on recognizing patterns in the moves,
Okay.
like noticing that you always have to move the smallest disc every other turn.
Interesting.
And then there was a strategy driven by visual perception, like noticing that a big disc is blocking a smaller disc that needs to be moved.
Okay, so it's like 3 different ways of seeing the same puzzle.
Exactly. And what's fascinating is that each of these representations, they demand different things from our attention and from our short-term memory.
Like you're focusing on different aspects of the problem.
Right. And they also affect how well we can transfer what we've learned to a slightly different version of the puzzle.
So the way you think about it affects how you learn from it.
Exactly.
Yeah.
And more recent research using eye tracking has actually shown that when we look at the Tower of Hanoi, we really do see those stacks of discs as meaningful units.
We're chunking the information.
Exactly. Which makes sense. It helps us plan our moves more effectively.
Okay, so representation is crucial for puzzles. Now, when it comes to actually searching for a solution, means end analysis seems like a natural fit, especially for those transformation problems where you're taking an initial state and changing it step by step to reach a specific goal.
Yeah, you're spot on. Think of the missionary cannibal problem, or those water jug puddles where you have to measure out a specific amount of liquid using jugs of different sizes. In those cases, means-end analysis would be your go-to strategy.
So, like in a water jug problem, you're constantly checking how much water you have, comparing it to the target amount, and making moves that reduce that difference.
Exactly. And in more complex situations where there are a lot of possible moves, like trying to prove a theorem in logic, creating a table of connections can be really helpful for guiding this means-end analysis.
Okay, a table of connections, what's that?
It's basically a way of visually mapping out the different moves you can make and how they relate to the gaps you need to fill to reach your final conclusion. It helps you stay organized and focused.
Makes sense. So it's like a more structured approach to means and analysis.
Exactly. But remember, even with these tools, means-end analysis isn't always the most efficient strategy. It can sometimes lead you down a lot of dead ends, especially if the problem space is huge.
You mentioned the 4 sevens problem earlier, making 56 using only 4 sevens and basic mathematical operations.
Right. There, means-end analysis might not be so helpful because there are just so many possible combinations to try.
It's like trying every single path in a giant maze.
Exactly. So sometimes you need a different heuristic, like working backwards.
Okay, working backwards.
Instead of starting at the beginning and trying to reach the end, you start at the end.
And work your way back.
Right. So with the 4 sevens problem, you might start by thinking, okay, what are the factors of 56?
Interesting. So you're kind of reverse engineering the solution.
Yeah, exactly. Working backwards is especially useful when there are many ways to begin the problem, but only a few ways to actually arrive at the solution.
Okay, so we've got means end analysis for those step-by-step problems, and working backwards for those where the end state is more constrained. Now, what about sub-goals? We talked about those earlier in the context of the 5MC problem.
Right. Sub-goals, they're all about breaking down those big, scary problems into smaller, more approachable chunks.
Bite-sized pieces.
Exactly. And remember, Reed and Abramson's study showed that suggesting a specific sub-goal in the 5MC problem really helped people.
Yeah, the get 3 cannibals across first sub-goal.
Right. And their research suggested it wasn't just about making the search space smaller, it actually seemed to help people shift to a more effective strategy overall.
So the sub-goal was like a mental nudge in the right direction.
Exactly. They called this the strategy shift model. The sub-goal encouraged solvers to move away from a less effective strategy, like trying to keep the number of missionaries and cannibals balanced on each side, and move towards a more goal-directed approach, like means-end analysis.
Okay, so sub-goals can be pretty powerful, but I imagine it's not always easy to identify useful sub-goals from the start.
You're absolutely right. Sometimes it's obvious, sometimes it takes a bit of exploration, and sometimes you might set a sub-goal that turns out to be a dead end. And as Hayes pointed out back in '66, even after reaching a sub-goal, you might feel a bit lost and unsure about what to do next.
It's like reaching a checkpoint in the maze, but not knowing which way to turn next.
Yeah, exactly. But even with those challenges, sub-goals are still a really valuable tool for making complex problems more manageable.
Okay, so we've talked about representation, search strategies, and sub-goals. What about analogy? Using solutions from past puzzles to help us solve new ones.
Right. And with analogy, we need to distinguish between a few different types of similarities between problems. We have what are called isomorphic problems. Those are problems that are structurally identical.
Like twins.
Exactly. But they might have different surface features.
Okay, so the underlying logic is the same, but the details are different.
Exactly. And those Tower of Hanoi variations that Hayes and Simon studied are a great example of this.
The ones with the monsters and the globes.
Yeah. They found that even though the underlying rules were exactly the same as the standard Tower of Hanoi, the specific details of how those objects moved could actually affect how easy people found the problem and how well they could transfer their knowledge from one version to another.
Interesting. So even small changes in the presentation can make a big difference.
Absolutely. And it's not always the straightforward one-to-one mapping between the moves you make in one problem and the moves you make in the analogous problem.
Okay.
Reed and his colleagues did a study where they looked at the transfer of knowledge from the 3MC problem, 3 missionaries and 3 cannibals, to the jealous husbands problem.
Oh, yeah. The one where the husbands are jealous of each other and you can't leave a wife alone with another husband.
Exactly. And they found that while some moves in the 3MC problem had a clear, unique counterpart in the jealous husbands problem, the reverse wasn't always true. So the transfer of knowledge through analogy, it can be a bit asymmetrical.
Interesting. It's not always a perfect mirror image.
Right. Now, finally, we have schema.
Schema. Those mental shortcuts.
Right. But with puzzles, we often don't have ready-made schemas available because we're usually encountering these puzzles for the first time.
Right. They're new challenges.
But Gick and Holyoke, they found that comparing analogous puzzles
Side by side.
exactly, that can actually help us build schemas over time. By noticing the common structure, the underlying logic that connects these different puzzle scenarios, we start to abstract a general problem-solving approach that we can then apply to new, but structurally similar puzzles.
So, learning by comparing. It helps us see the forest for the trees.
Precisely. And this idea of comparing examples to extract general principles, that's a powerful one that applies to a lot more than just puzzles.
Okay, so that was a whirlwind tour of well-structured problems. We talked about their defining characteristics, the mental models we use to represent them, search strategies like means-end analysis and working backwards, the power of sub-goals and analogies, and the role of schemas.
And how all of that plays out in the world of puzzles.
Now, let's shift gears and venture into the murkier, fuzzier realm of ill-structured problems.
Okay, ill-structured problems. The Wild West of problem solving.
ISPs for short. So Jonason, he described these as problems with multiple possible solutions and uncertainty about which concepts and rules are even necessary to solve them.
Right, so unlike those neat, well-defined puzzles.
Where you know the rules of the game.
With ISPs, the goalposts might be moving, the rules might be unclear, and there might not even be a single right answer.
It's more about finding a good solution
Or a better solution.
than the one you had before.
Exactly. So think of things like design challenges.
Trying to design a new product or a building.
Or tackling those complex ethical dilemmas where there are trade-offs and no easy answers.
Right, where different values might be in conflict. So how do we even begin to approach these kinds of problems? They seem so messy and open-ended.
Well, that's where the Gestalt psychologists, they offer some really interesting insights.
Okay, the Gestalt psychologists.
They were really interested in these insight puzzles, these problems where the solution often comes to you suddenly.
Like a flash of inspiration.
Exactly, after a period of feeling stuck. And they emphasize this idea of perceptual reorganization, of mentally restructuring the problem, seeing it from a new angle.
Ah, so it's about breaking free from your initial way of seeing things.
Precisely. And those classic insight puzzles like the matchstick problems,
Oh, yeah, where you have to move matchsticks to make a mathematical equation true.
right, or the nine-dot problem.
The one where you have to connect 9 dots with 4 straight lines without lifting your pen?
Exactly. Those are great examples of how our initial perception of the problem can actually limit us.
And the solution often involves thinking outside the box, literally, in the case of the 9 dots.
Exactly. Gold described the problem space of these insight puzzles as broad but shallow.
Broad but shallow, what does that mean?
It means there are a lot of initial possibilities.
A wide search space.
Right. But once you have that key insight, the path to the solution is usually pretty straightforward.
It's like finding the right trailhead in a vast wilderness. Once you're on the trail, it's a clear path to the summit.
Perfect analogy. But the trick is finding that trailhead. And that often requires a shift in how we're representing the problem.
Okay, so let's talk about representation in the context of these insight puzzles. It seems like it's all about breaking free from those mental constraints we impose on ourselves.
Exactly. Like with the matchstick problems, we often assume that we can only move the matchsticks to create valid arithmetic equations.
We get stuck in our usual way of thinking.
Right. And with the nine-dot problem, we tend to keep our lines within the imaginary square formed by the dots.
Even though the instructions never actually say we have to.
Exactly. Knoblich and his colleagues, they did a lot of research on these kinds of problems, and they found that people often impose unnecessary constraints on themselves, making the problem harder than it needs to be.
So the first step is to question your assumptions.
Precisely. Challenge those self-imposed boundaries. And then there's this fascinating phenomenon of incubation,
Incubation.
taking a break from the problem.
Stepping away from the puzzle.
Exactly. And there's a lot of evidence suggesting that this can actually help you solve insight problems. CO and Ormerod, they did some meta-analyses.
Okay, meta-analyses. So they looked at the results of many different studies.
Right. And they found that incubation can help in a few ways. First, by allowing your brain to make connections you might not consciously be aware of.
So like your subconscious mind is working on the problem in the background.
Exactly. Second, by weakening those incorrect solution paths that you might be stuck on.
So you're less likely to fall back into those mental traps.
Right. And third, by allowing your mental representation of the problem to reorganize itself.
So you might come back to the problem with a fresh perspective.
Exactly. And there's also some really interesting research connecting mind wandering to insight.
Mind wandering. So like letting your thoughts drift.
Right. Zedelius and Schooler, they found that in those compound remote associates tasks.
Where you have to find a word that connects 3 other words.
Exactly. People were more likely to solve those problems when they were allowed to let their minds wander before trying to solve them.
So it's like giving your brain some space to roam around can actually lead to those aha moments.
Exactly. And Gilhooly and his colleagues, they found that doing a dissimilar task during incubation.
So like doing something completely different.
Right. That can be even more beneficial for insight than just passively resting.
Makes sense. It's about getting out of that mental rut.
Exactly. So incubation, taking a break, letting your mind wander, doing something different, all of these things can help you break free from those initial constraints and see the problem in a new light.
Okay, so we've talked about how the representation of the problem can change during incubation. What about the search process itself? How is search different in these insight puzzles compared to those step-by-step transformation problems?
Well, Metcalf and Wiebe, they found that with transformation problems, people generally have a pretty good sense of how close they are to the solution.
They feel like they're making progress.
Exactly. But with insight puzzles, it's different. Their feeling of warmth, of getting closer to the solution, it often only spikes right before they have that sudden aha
Moment. So it's like you're stumbling around in the dark and then suddenly the light comes on.
Exactly.
Right.
And this difference in how we experience the search process, it fits with the idea that in many insight puzzles, the goal itself isn't clearly defined,
Okay.
like with those classic arrangement problems.
Arrangement problems.
Yeah, those are problems where you have to rearrange things in a specific way to achieve a goal. But the goal itself might not be obvious from the start.
Okay, I'm intrigued. Give me an example.
So think about Kohler's classic study with the chimpanzee and the bananas.
Oh yeah, the chimp had to figure out how to stack boxes to reach the bananas hanging from the ceiling.
Exactly. Or Dunker's candle problem.
The one with the box of tacks, the candle, and the match.
Right. You have to figure out how to attach the candle to the wall so it burns properly.
Using only those materials.
Exactly. Now, in both of these problems, the goal is there,
Get the bananas, mount the candle.
but it's not immediately obvious how to achieve it.
And that makes it difficult to use means-end analysis, right?
Exactly. Because with means-end analysis, you're constantly comparing your current state to the desired goal state.
And making moves to reduce that difference.
But if the goal state itself is unclear, then it's hard to know which moves will get you closer.
So how do we solve these arrangement problems?
Well, Besak and Novick, they argue that we can actually apply a blend of representation and search, even to these seemingly pure insight problems.
Okay, so it's not just about restructuring the problem, but also about actively exploring the possibilities.
Exactly. They use the 9-dot problem as an example.
The one where you have to think outside the box.
Right. And McGregor and his team, they proposed a model where we subconsciously keep track of how many unconnected dots each line we draw connects.
Okay.
And when we realize that our current approach isn't working,
And we're not making progress.
then we relax those self-imposed constraints.
Like the constraint of staying within the imaginary square.
Exactly. And that's when the insight occurs.
So it's like hitting a wall in the search process triggers a shift in representation.
Precisely. And this idea of constraint relaxation, it's been used to explain solutions to other insight puzzles as well, like the 8-coin problem, where you have to move 3 coins to form 2 rows of 4.
You have to stack some of the coins.
Exactly. The solution involves breaking the no stacking rule that people often assume.
So again, it's about questioning those assumptions.
Right. And Jones, he did a study using the car park problem.
The one where you have to figure out what number is underneath a parked car.
Exactly. And he found evidence for both progress monitoring
So people were keeping track of how close they were getting.
and changes in representation.
But the change in representation seemed to be more important for actually solving the problem.
That's what his findings suggested. And Ash and Wiley, they did a study using variations of the 8-coin problem. And their research hinted that this restructuring of the problem in your mind, it might actually happen more automatically than we realize.
So less conscious effort involved.
Compared to the more deliberate step-by-step search we might use in other types of problems.
Interesting. So it's like sometimes the solution just pops into your head.
And Healy and Son, they proposed this really comprehensive theory of how insight occurs.
Okay, lay it on me.
They called it the explicit-implicit interaction theory.
Implicit. So like a combination of conscious and unconscious processes.
Exactly. And they developed this computer model called Clarion that simulates how these processes might work together.
Interesting. So what does Clarion tell us about insight?
Well, it outlines 4 main stages of problem solving.
4 stages.
First, there's preparation. This is where you consciously gather information and try to understand the problem.
Okay. Expert speaker.